Good morning, students. This is Habeeb Rani, Assistant Professor of Mathematics from Haji Kartarautar Haudia College, Uttamapalayam. Today, my topic is countable set in modern analysis. Let us see some definition. So here we use the definition of equivalent. If the two sets are said to be equivalent, if there exists a bijection F from A to B. Here we take two sets A and B. A and B are said to be equivalent. We define the map F from A to B. If there exists a bijection from A to B, then we say that A and B are equivalent, or A is equivalent to B. Let us see one example. Here the set A as n, set of all natural numbers, and B equal to 2, 4, 6, etc. to n, set of all even numbers. So if we define the map F from A to B by F of n equal to 2n. So obviously this map is a bijective map. If the map is bijective, it satisfies the condition 1, 1 and on 2. Here we put n equal to 1, we get 2, n equal to 2, we get 4, n equal to 3, we get 6. So every image has a pre-image and every image has at least one pre-image. Hence, there is a bijection map from A to B. A is a set of all natural numbers. Hence, if there exists a bijection, the two sets are said to be equivalent. So here A is equivalent to B, even though A has actually more elements than B. Next definition. A set is said to be countably infinite if A is equivalent to the set of all natural numbers. So already we see the definition of equivalent condition. If any set which is equivalent to the set of all natural numbers n, then that set is said to be countably infinite. Let us see the definition of countable. A set A is said to be countable if it is finite or countably infinite. We know every finite set is countable. We can count the elements or we can label the elements. Also, countably infinite set is also countable. What do you mean by countably infinite set? If there is a bijection map from A to n, that is A is equivalent to n, then A is said to be countably infinite. See, example 1. Already we see set of all even numbers is countably infinite. Therefore, it is a countable set. Another example is set is countable. Also here we take the set A equal to 1 by 2, 2 by 3 and 3 by 4. So here we define the map F from the given set A from n to A, which is defined by F of n equal to n by n plus 1. Clearly, this map is a bijective map because 1, 1 and on 2 condition is obviously satisfied. So if there is a bijection from n to A, then we say that A is equivalent to n. Any set which is equivalent to the set of all natural numbers n, that set is said to be countably infinite. Every countably infinite set is countable, hence A is countable. Let's see one theorem. A subset of a countable set is countable. This is very interesting theorem. So, see, here we take one countable set named as A. Let A be a countable set. And we choose subset of A, that is B. B is a subset of A. So, here we have to prove that B is countable because B is the subset of A. So, we have to prove that B is countable. So the first one, if A or B is finite, then obviously every finite set is countable, therefore B is countable. If A is finite, B is a subset of A, therefore B is also finite, hence B is countable. That case is over. In another case, if A and B both are infinite, so A infinite means already given that A is countable. So it must be countably infinite. So we can write the elements of A as A1, A2, etc., AN, etc. So here we choose the subset B of A. So we select one element AN1. It must be the first element in A such that it also belongs to B. Next, we choose another element AN2. It be the first element in A which follows AN1 such that AN2 belongs to B. But AN2 is the second element in B. So in similar manner, we can label the element in B, that is first element, second element, third element. Now we take all the collections of this element. Thus all the elements of B can be labeled by using the elements of natural numbers. Hence B is countable. Are you clear? Okay. Next theorem, n cross n is countable. So we have to prove n cross n is countable. Before going to prove n cross n is countable, you must know about the elements of n cross n. So n cross n is nothing but the set of all elements of the form ordered per A comma B such that A and B belongs to natural numbers n. Set of all natural numbers n. A must be a natural number and B is also a natural numbers. We take the order per A comma B that must belongs to n cross n. First, we select the order per A comma B such that the sum of these two elements must be equal to 2. That is A plus B equal to 2. We get only one pair. Such a pair is namely 1, 1. Next, we take all order pairs A comma B such that A plus B equal to 3. We have two pairs, 1, 2 and 2, 1. Similarly, we take the next order pair A comma B such that A plus B equal to 4, proceeding like this, and also listing all the set of elements and omitting those elements which are already exist. So clearly, every element, every ordered pair in the set must be exactly once exist. So this set contains every order pair belonging to n cross n exactly once. So there is no element repeated. So we can label the elements of n cross n. Hence n cross n is countable. Next theorem, if A and B are countable set, then we have to prove A cross B is also countable. So the proof is very interesting. Here the two sets are countable set, A and B. We have to prove the Cartesian product A cross B is also countable. So already we know any set which is equivalent to set of all natural numbers here, that set is countable. If it may be one set means. Here we take Cartesian product of two sets, A cross B. So here we know that already n cross n is countable. So we define the map from n cross n to A cross B. If the map is bijective, then A cross B is equivalent to n cross n. But n cross n is already countable. So any set which is equivalent to the countable set, that set is also countable. In this manner, A cross B is also countable. See the proof. Here we assume that A and B are countable. By the definition of countable, it may be finite or countably infinite. Let us choose, let A and B are countably infinite. So we named the sets A equal to A1, A2, etc. AN and B1, B2, B equal to B1, B2, etc. BN. Now we define the map F from n cross n to A cross B. We defined by F of I comma j equal to AI comma Bj. Listen, here the defining the map is very important. Here we define F of I comma j equal to AI comma Bj. If I take 1 comma 2, I equal to 1, j equal to 2, then F of 1 comma 2 equal to A1 comma B2. So our aim is to prove F is a bijective map. So here, first condition 1, 1. 1, 1 condition is we take the image is equal, then pre-image is also equal. F of x equal to f of y, we get x equal to y. Then f is 1, 1. So first we choose two elements, x and y in n cross n. Domain la and element choose pandinga, n cross n. So x equal to p comma q belongs to n cross n and y equal to u comma v belongs to n cross n. So we choose the condition f of x equal to f of y. We know if p comma q belongs to n cross n, then f of x equal to ap comma bq, f of y equal to y is u comma v, then f of y is au comma bv. F of x equal to f of y, that implies ap comma bq equal to au comma bv. If the two ordered pairs are equal, x coordinate must be equal and y coordinates must be equal. So ap equal to au, bq equal to bv. So if the two elements are equal, then the bases are same. P equal to U and Q equal to V. So we get P comma Q equal to U comma V. P comma Q is U and U comma V is Y. Therefore, X equal to Y. Hence F is 1, 1. Hence F is onto. Now choose the element am comma an belongs to codomain A cross B. Then there exists an element m comma n in the domain n cross n such that f of m comma n equal to am comma an. This is the condition of onto. Hence f is onto. So f is 1 1 and onto. F is a bijection. The map is bijection. The two sets are equivalent. Therefore A cross B is equivalent to n cross n. Already we know that in theorem 1.4 n cross n is countable. Any set which is equivalent to the countable set, that set is also countable. Therefore A cross B is countable. Hence proved. Thank you, students.